Good afternoon. This is our last lesson on process control. Today we will look at some special control structures, special in the sense that so far whatever controls we have studied, PID control, Smith predictor control, everywhere we had sensed one particular process variable which we wanted to control, that is the output, and we fed it back, and we also used only one actuator. Now today we will see that in some cases situations arise where we can use more than one sensor in a process, or there are sometimes more than one actuator also. So we will take a brief look today at those kind of control structures, and we will also see what kind of advantages can be derived by these. So that is the objective. In particular, we'll study cascade control, which is a very popular control strategy. We'll study something which is known as override control, selective control, and split range control. These are very standard terminologies found in process control books. So we'll take a look at that, right. So before we do that, let's first see the instructional objectives. So today, after learning this lesson, the students should be able to describe some drawbacks of single loop control, and based on some of these drawbacks we can see that cascade control will address some of these drawbacks, and therefore we will learn cascade control, and he should be able to draw a cascade control loop and demonstrate the advantages of this structure over a single sensor feedback loop, conventional. Additionally, he will also be able to understand what are selective and override controls, and similarly for split range controls. So the basic idea is to familiarize ourselves with this kind of control loops and understand their advantages. So first we will take a look at the problems of single sensor control loops. Sometimes it happens that the basic idea of a control loop is to correct or adjust the control input to take care of the disturbances. Basically they are, and a standard control loop does it by computing a control law based on the error. So how quickly the control loop will be adjusted in response to a disturbance depends on how quickly the error will be formed. So for example, we have found that in our single sensor control loops, for example, in our let us take the standard control loop. So you have the reference coming here, and here you have the controller C and the plant P, and this is the output, and there is a feedback. So you see that there may be disturbances acting on the plant at various points, right. So these are disturbances D, this is the set point R, and this is the output Y. So the controller basically calculates this U, which is the control input, to either take care of take care of basically variations in either R or D. So if R is changing, then it needs to adjust U so that Y becomes close to R. Now we see that this controller does well, because any change in R, if R changes from this level to this level, let us say, then immediately the error will also jump from this level to this level. So the change in error E is almost instantaneous corresponding to the change in R. So, the controller also responds with an instantaneous change in U and the output gets adjusted as quickly as possible. But that does not happen when there is a change in disturbance level. So, because even if you have a, let us use a different color of the pen. So, even if you have a disturbance D changing here, the effect of this disturbance to come on the output takes some time, because the disturbance has to enter through the plant and then travel to the output. So, during that time the error E remains unchanged and the controller does not obviously adjust its input. So, this is a problem of single loop control. Okay. So, having understood this, we can realize this, that high lag between error disturbance and output can sometimes occur depending on where the disturbance is appearing. The next point is that now we know that if there is high lag, then our phase margin is low, that is the system loop transfer function has lot of phase lag. So, therefore, we need to keep our gains lower to maintain stability. Now, if we have to keep our gains lower, naturally we will get poor transient response. So, we are not driving the plant hard because of stability requirements, right. So, this is a problem which arises in single loop controls sometimes. Secondly, this is a problem which we will address, we will see how it can be addressed by using cascade control, and very commonly addressed. Now, there are some other situations in control. For example, in some cases we have to control a variable which exists over a distributed, spatially distributed region. For example, suppose we want to control the temperature in this room in which I am sitting. So, obviously this room is a big place where I mean how do you control the temperature in a room? Typically in air conditioning you provide cold air. Now, how much cold air you will provide depends on what temperature you want in the room. But how do you give feedback? Obviously using temperature sensors, but a temperature sensor will, suppose it's an RTD. Typically in air conditioning temperatures are sensed using resistance temperature detectors. So, where will you put the resistance temperature detector? Will you put it on the ceiling or will you put it on the floor? If it is on the floor, which corner of the floor, or would you put it in the center? So, remember that you will be controlling the temperature at exactly the point where the sensor is put. Even if the temperatures at the other places are slightly different, the controller has no way of knowing that, because the sensor is the controller's eye. So, therefore, whenever we are having a sensors, we should understand that we are controlling the controlled value at that sensor location. So, if you want to maintain some uniform control over region, sometimes we need to put more than one sensor and incorporate them in a control loop. So, this is a requirement in many cases. So, therefore, multiple sensors at different locations are needed to control the overall process average. So, you want to control the average temperature of the room. So, you have to put 3-4 sensors at 3-4 different locations, or sometimes we want to control extreme values, because sometimes the output at various places may not be the same, and if it goes too high it may cause damage, or if it goes too low it may cause damage. So, sometimes we may like to choose average values, sometimes we may like to choose extremal values, that is maximal or minimal values, and for these purposes we need to put multiple sensors. There are also some cases where systems are actually operated in different modes, that is when it is in, suppose the set point is very low, then you want to operate the system in one mode. If it is very high, you want to operate it in another mode. Typically happens because processes are non-linear. For example, if you want to in if you go to western countries, then you will find that part of the year the temperature becomes warm. So, you need air conditioning or you need cooling, and part of the time when it becomes I mean in winter you have to heat the room. Now, you see cooling and heating cannot be done using the same equipment. So, you essentially for controlling the same process variable, that is the room temperature, you need two different sets of equipment or actuators, and you need to have a control loop which will incorporate these two actuators and actuate any one of them depending on the set temperature that you want, that is whether the set temperature is less than ambient or is it more than ambient. So, in such situations certain changes to the loop structure has to be made, and we are going to study that. So, let us first look at cascade control. So, we are first going to look at the at a motivation for cascade control. So, here we have a imagine a process, right. So, here we have a process. So, this is our plant. Now, we are just imagining that the plant is actually consisting of two different subsystems. Presently, we see examples. We will see examples very shortly. There are many cases. For example, cooling of reactors is a very typical case, where the relationship between the input, typically reactors are cooled using coolant liquids which flow through jackets of the reactor. So, the reactor has some space in its wall, and you circulate coolant through that space, so that you can cool the temperature of the reactor. This happens for exothermic reactors where the reaction itself produces heat. So, the input is the steam flow rate, and the output is the temperature of the reactor which you want to control. So, how does the steam flow rate translate into a temperature? So, there are various stages. So for example, first if you put not steam flow rate, coolant flow rate. So, first the coolant flow rate will establish a temperature in the jacket. Then, because there will be temperature difference between the jacket and the reactor interior, so there will be heat transfer, and heat will come from the reactor to the jacket, and therefore the temperature will fall. So, there are basically two different mechanisms. One is from flow to establishment of temperature in the jacket, and from jacket to affecting that is from the jacket, between the jacket and the reactor heat transfer mechanism. So, such things happen, and you have, for example, in a motor suppose you want to control position. So, you give what do you give? You change the electrical voltage at the terminal of the motor. So, the voltage suppose it's a DC motor. So, basically you change the armature current. If you change the armature current, then what you change is torque. So, basically the input that you are giving is torque. Now, so here you have torque, and here you have position, suppose a position control application. So, from torque is directly proportional to acceleration. Just divide by moment of inertia, you will get acceleration. So, that is constant, but between acceleration and velocity there is one integration. So, this could be integration 1 by s, and here you have velocity. Again, between velocity and position you have another integration. So, this is another 1 by s, and you get velocity and you get position. So, you see that the between input torque and output position you have two different subsystems. In this case, in the case of a motor, it is an integral. So, this is a very typical situation. Now, in this situation there can be disturbances everywhere. For example, there can be load disturbances. So, and where does the load disturbance come? The load disturbance can come in various places. It can, in this case, in the case of the motor, it can come at the input itself, because total electromagnetic torque minus load torque will give you the net torque. So, if a load disturbance comes here, this must traverse through this whole process and then it will affect the output and then it will be feedback and then there will be error. So, it takes a lot of delay. This is the reason why. So, what happens is that if you have so much of phase lag then sometimes what can happen is that you see the stability margins are lower. So, disturbance d2 to y transfer function has lag, and but it so happens that this intermediate variable y1 is immediately affected by d2 in this case, or even if the disturbance is acting here, the transfer function between the disturbance here and the measurement and the variable y1 has much less lag than the transfer function than the lag between this disturbance and this out. So, now this is an observation. So, here is an intermediate variable which we are not using. Maybe it could be measured, maybe it could be measured very simply. For example, in the case of the cooling reactor, suppose we could measure the jacket temperature. Why not? That involves simply putting a temperature sensor. Similarly, most position control loops have speed feedback. So, measuring the shaft speed requires simply putting some kind of a tachometer or speed encoder. They are not very difficult to measure. The advantage is that now we have another measurement. So, you see that. So, the question is that if we could measure some intermediate variable y1, then feeding it back, does it give any advantage? Actually, it gives plenty of advantage. You can give significant improvement in response to disturbance, also improvement in transient response to set point changes, because the controller gain can be significantly enhanced. So, that is achieved by cascade control. So, how? Let us see that. So, we look at cascade control. Okay. So, now what are we doing? So, let us look at this. First of all, suppose we have decided that there is some intermediate variable y1 which I am going to measure and I am going to feed it back. So, you see that now the y feedback loop, this is the outer or primary loop, which is a standard loop. In addition to that, inside the loop we have put another loop which we call the inner or the secondary loop. Now, what is the function of the secondary loop? There are several interesting functions. Firstly, if you look at it from the primary loop point of view, so now previously it was in the loop there was C1, GP2 and GP1. Now, you have in place of GP2 you have GP-2, which is the closed loop transfer function of this inner loop. Previously you had only this GP2. So, what is the difference between G-P2 and GP2? Firstly, G-P2 has much less phase lag. That is always true because of the fact that closed loop systems have much less phase lag than open loop systems. So, this has much less phase lag, which means that if you look at it from an outer loop point of view, this C1 G-P2 GP1 combination, the overall phase lag has now reduced. So, if it has reduced, then the value of C1 which can be increased, this value of the gains of the controller can be increased, right. So, C2 can right. Now, which means that overall transient response will increase because now R, any set point change in R will be acted upon much faster by C1 because it has higher gains. So, that is a very good advantage. So, which means that we must design this loop such that this G-P2 has significantly lower phase. So, when can we do that? So, when does a closed loop system have low phase? When C2 is high. You see, closed loop transfer function is what? It is G2 C2 by 1 plus G2 C2 is the closed loop transfer function of the inner loop. So, if C2 can be made high, then this becomes almost equal to 1. So, the phase lag reduces to 0. So, we should be able to use a high C2, but can we use a high C2? Yes, we can, because as far as this loop is concerned, this loop phase lag is only GP2. Previously, the outer loop we are having problem because the phase lags of GP2 and GP1 were actually adding up. But now in the inner loop, we have only the phase lag of GP2 to take care of. For example, as far as our motor control is concerned, GP2 has maximum has around 90-degree phase lag. So, if something has a 90-degree phase lag, it is a first order process, then we can theoretically speaking, we can use very high gains of C2. And if we use very high gains of C2, then this closed loop transfer function will be almost equal to 1. So, it is indeed possible to have for C2 to have okay. So, since inner loop phase is low, much lower, it is often possible that C2 can be very high gain, and then the outer loop phase is also reduced significantly, and therefore C1 can be of high gain. So, that is the point. Second thing is that previously we were thinking that this response of D2 travels to Y much slower. So, taking care of D2 takes time. Now, what happens is that the effect of D2 or even the effect of, let us say, if we have some disturbance here, like in the case of a motor, the time it takes from here to here is much lower than that from here to here. Similarly, from here to here is, from D2 to here is immediate. So, and since this loop has very high gain, so therefore the effect of disturbance either here or here gets very quickly corrected in the inner loop itself, and it does not travel to the outer loop. So, we have been able to contain the disturbance within the inner loop, and we are able to stop it from spilling over to the outer loop. So, the effects of inner loop disturbances are neutralized very fast in the inner loop. These are very significant advantages, and as is said here, so the outer loop phase is low, so C1 can be high gain and better transient response for the overall system. So, you see that you have several advantages. You have better stability margins, you can contain inner loop disturbances within the inner loop, and they will not affect the output, they will get corrected in the inner loop. And thirdly speaking, your overall transient response will improve because you can use higher gains in the outer loop, right. And all this you are getting at the expense of an additional measurement, number 1, and number 2, a slightly more complicated control law. So, these are often very low prices to pay for a better control of the process. Therefore, they are very widely used. We will look at an example, a practical example. So, what we are having here is that we want to control, this is a kind of an exothermic reactor. So, we want to control the temperature of this reactor, this is what we want to control. So, obviously, we are giving a feedback here, this is the outer loop. So, this is the outer loop feedback or primary loop feedback. Now, initially, let us assume that this is not there. So, you see, we could actually do away with this and actually use, in our single loop control, we could remove these parts. This feedback is not there, we could use that, and we can have a normal control loop. So, what are the disturbances? The disturbances are, there could be several disturbances. For example, there could be a feed temperature TF, which will cause temperature of TR to temperature of the reactor to change. This is a disturbance which will get quickly affect TR. There could, this there could also be a disturbance in the coolant temperature. The coolant itself, we are controlling the flow rate of the coolant, but the temperature of the coolant is not known, probably that is not in our hand. So, the temperature of the coolant itself could act as a disturbance, and this will take a lot of time to travel to TR, because first of all this has to change, this temperature coolant will have to change the temperature of the whole jacket. That itself is a heat transfer and mixing process. Once that jacket temperature is changed, then through another heat transfer process the reactor temperature will change, and then only feedback will go, and then only the flow rate will get affected. So, now instead of that, if we use so now we are going to use the use of cascade control loop. So, we have made another measurement. Okay. One moment please. I want to take care of the eraser. Oh, okay, I got it. Yeah. So what we have is, instead of that we have a cascade control loop, where we are now incorporating this additional measurement called the jacket temperature, and we are feeding it back, right. So, this is this is my secondary loop, or inner loop, and this is my primary loop. So, now what I am doing is I am giving, so the primary loop feedback is there is error, it is coming to the first controller. So, this is my C1, and this is another temperature controller which controls the jacket temperature, that is my C2, and finally this is my U. Now, what happens is that if there is a coolant temperature change, then that will affect TJ much faster and it will get fed back, and therefore, the flow rate will automatically get changed very quickly, even before it can start affecting the reactor temperature. So, this is the, so here in fact I mean such temperature control loops in chemical processes are almost without exception they are cascaded. Just like in motor position control loops, you always have a velocity feedback. It is very rare when you do not have cascade control. So, we come to the so this is I am trying to model that situation basically. So, it shows how things are. So, delta Fc, which is the change in the flow of the coolant, first so that excuse me. So, so this just shows that this delta Fc affects this delta Tj through the jacket. Similarly, this delta Tc, in fact actually these effects are this flow and temperature, these effects are actually multiplicative. So, I have considered their increments so that they become additive. So, so this shows that this delta Tc also affects delta Tj, and then once delta Tj is established, then between delta Tj and delta Tr there is a reactor heat transfer dynamics, and similarly the feed temperature change also affects the reactor dynamics. So, this is one disturbance D1, this is the other disturbance D2, and we are giving a feedback around this jacket and again another feedback around the reactor. So, basically this is explaining that thing. Then so this, having understood cascade control, we see some remarks that important remarks is that firstly secondary loops can use P controllers. Why? We know that P controllers can result in steady state errors. So, but it so happens that, for example, firstly the secondary loop output is not a real output. So, even if there is a steady state error, we are not interested as per se to control that output. Secondly, we have already seen that if there is a steady state error, what is the one way of going around it is by increasing the set point. So, suppose in a control loop, if you give 100, there is some steady state error because there is some proportional controller, and here you get say 95. You know that you get a steady state error in this loop. Then one way of getting around this problem is that you, rather than giving 100, you give 105. If you give 105, you will probably get something very close, 99.7 or 8 or something you will get. So the technique is that you adjust the set point. Now, for the inner loop, who adjusts the set point? That the set point is adjusted by the outer loop. So, interestingly, if there is a steady state error, then what will happen is that the outer loop will slowly adjust the set point to the inner loop and the steady state error will vanish. So, therefore, you can use P controllers. The second typically flow control loops are often secondary loops, and there is also a significant advantage because these flow control devices called valves are sometimes very significantly nonlinear. So something which is nonlinear means what? See, all the time we have various nonlinear systems and we are looking at them, we are trying to analyze them using linear control theory. So, which means that we are using, they are incremental characteristics, that is, we are taking local loops and then we are considering local slopes in their characteristic and we are considering them as the gains. So, the valve incremental gain changes considerably depending on in which region of flow you are operating. So, now and remember that you have lag, so you want to keep the overall process gain lower. So, and this process gain keeps varying because the valve gain keeps varying. So, how do you design a controller? So, to design a controller, you will have to make a conservative estimate of the controller gain, so that even for the highest valve gain it will not go unstable, right. But what happens here is that since the valve is in the inner loop, so the inner loop controller, imagine what is the job of closed loop control. See, the job of closed loop control is such that even if there is a variation in the process gain, the closed loop transfer function is not affected. So, the closed loop, so the valve variations are actually taken care of in the inner loop, and in the outer loop you can design a, so the inner loop characteristic, closed loop characteristic varies much less because of valve gain variations, and you are able to make a much better estimate of the controller gain. So, this is the advantage, this is another advantage of cascade control. But for cascade control to be effective, we must remember that this overall phase lag must be well distributed over this GP1 and GP2, because suppose that GP1 is a constant K, it has no phase lag and all the phase lag is in GP2. Then what happens? Then what is the idea of giving a feedback here? See, then the feedback of the open loop plant gain of the open loop plant and loop gain of the closed loop loop phase are same, because both are constants. So, therefore, the problem of loop phase still remains and the whole problem will come in the outer loop. So, it is becoming like the old case. Similarly, if you put this one as k, if you put this one as k and this one as GP1 and put all the phase lag here, then the problem will be to decide the inner loop. So, the inner loop controller will now have the same stability problems as the overall process. So, in such situations cascade control does not work well, or in other words this. So, what do you do? So, you have to choose a variable. So, the variable that you choose to feed back in cascade control should be very judiciously chosen. It should be chosen such that it divides the plant into two sub processes of balanced phases, right. Then the cascade control loop will actually work well. So, and well, there are several other issues which we are not going to consider here, but there may be, for example, there may be issues of saturation of actuators, there will be issues of frequency detuning of the inner loop and the outer loop, that is when the overall gain will peak at some frequency in the closed loop in the inner loop and some other frequency in the outer loop. So, such as they are more complicated issues of design, and we need not look at them at this stage.